Okay, so this is week 6 Tuesday in class homework that we're going to go over. And basically, this front page is just going to be looking at a specific reaction. And then this first question, though, is we're going to draw and practice naming ethers because ethers have a little bit of a different way how to name them. So we know IUPAC names. That's exactly what we were learning like last semester in Orgo 1. Pretty simple. We know how to do that. It's more so it's more traditional IUPAC naming, I would say, than the ether name, because everything has an IUPAC name but not everything has an ether name, if that makes sense. So that's why I would say that the IUPAC name is more traditional in a sense. So for number 1, we're actually drawing one ethers that we have not seen on this paper or in notes, which I'm going to draw just 2 examples right here, and I'm going to show us how we are naming them. So for this first ether, this is the first molecule that I'm going to name. There are many other ones that we could name in practice naming, but I'm just going to use the ones that I know are correct because Dr. G checked them in class. So IUPAC name is, we know this is a cyclohexane because there's no double bonds. That's why that has the ANE at the end. And we know that at carbon 1, there's a bond to an oxygen that's bonded to a tert-butyl. So this whole thing right here will be a tert-buoxy group because kind of like a methoxy or an ethoxy, it takes this, so that but, and adds an oxy at the end. So this whole thing, IUPAC naming, this will be a tert-buoxy. And then this will be a cyclohexane. And this is for IUPAC naming. So then we know that this cyclohexane is that parent name, so that's going to stay at the end. This is going to go first. And we could name it 1-tert-butyl buoxy cyclohexane, or we could simply just say tert-buoxy cyclohexane. Either way is fine. So I'm just going to write it with that one just so you know that you can write it both ways. But in this case, if you didn't add the 1, it'd be fine because that tert-buoxy is on carbon 1. So that's the IUPAC name. Now for the common name, an ether is simply an oxygen bonded to 2 R groups. And when we do focus on the ethers, what I like to do is focus on this oxygen and then kind of go off what's then bonded to the oxygen to get the ether name. So in this case, for this side of the oxygen, we have a tert-butyl. And then on this side of that oxygen, we have that cyclohexane. And the common name, then the parent name, is actually going to be the ether. So this is no longer the parent name. The parent name is ether. Now, to figure out which one of these goes first, we look at which comes first alphabetically, which in this case, C comes before T. So cyclohexane is going to be first, then tert-butyl, then the ether is going to be that parent chain at the end. So if we named this correctly, that's how we would name this molecule: cyclohexane, tert-butyl, ether. So let's look at this next example right here. It's a little different, but we do know how to name this. So now let's look at the IUPAC name first. IUPAC name is, this ring is going to be that parent name. So this whole ring is a benzene. And then this right here is that, like I said before, how we know what a methoxy is. This is a methoxy. So in this case, this would be a methoxy. And same thing, this is on carbon 1. So we could either name it 1-methoxy or not. And then this is a benzene ring. And it has an ENE because it has double bonds. So for the IUPAC name, we know that this benzene is going to be the parent name. So that's going to happen. That's going to be the suffix. So when we name it, it's going to be methoxy and then the parent name, which is the benzene. Now, same thing with this past example when I was talking about how I like to look at ethers like this. So at first identify that oxygen and then identify the R groups in the carbon chain. That's exactly what we're doing. And this is that oxygen right there that we're going to be looking at. So on this side of the oxygen, we just have a methyl group. And then on this side over here, this is actually a benzene. So the name stays the exact same. And same thing, we're going to be looking at which comes first alphabetically to name the common name, which B comes before M. So this is going to be first, then methane, then 3 is going to be that ether, the ether. I don't know why I keep saying that. And that's the common name for that molecule. Now, this one right here, number 2, is actually going to be, we're going to be creating a mechanism. And first we're going to draw MTBE, which is a methyl tert butyl ether. I'm going to mess up that ether this whole entire video, just so you know. So just ignore that. And we know exactly how to draw this because we've figured out how to name it and we know how to draw it as well as we did in problem 1. So we know that an ether is an oxygen bonded to 2 R groups. So we know that there's going to be an oxygen in there. And then on one side is a methyl group, which we know a methyl group is simply just this. And the other side is a tert butyl, which we've actually covered in that top. This first example right here. So when we create this molecule, it's going to look like just like this. Methyl, and then we have that oxygen, and then we have the tert butyl. And that's MTBE, methyl tert butyl ether. Now, this part B is we're going to be looking at the starting materials, and we're going to look at the reagents through a Wilson synthesis. That's the very important part, is through a Wilson synthesis, because we know what the reagent's going to be because it says a Williamson synthesis. We know that it's going to be H negative. We know that. And in our notes we have, we could do sodium, we could do potassium, one of those positive ions. So for this one, I'm going to do sodium. And then we're going to use like chlorine. I believe we could probably even use bromine as well. And then we're going to use that, and it's going to be connected to whatever one we want to start, because this example right here actually has 2 ways that we could do this that's going to do the exact same. So if we wanted to start with this being the starting material and then adding that methyl group, we could definitely do that. And if we wanted to do this as the starting material and add that tert butyl, we could do that as well. So I'm going to show how to do both ways. So let's say we start with this. Then this reagent is going to add that tert butyl to that chlorine. So then it's going to be exactly like this. And that would be our starting material and reagents if we were starting with this and adding that tert butyl. Now, what if we were starting with that oxygen and that tert butyl and then adding the methane group or the methyl group? This is how that would look. We would simply have that oxygen, and we would have that tert butyl, and then same thing. We'd have just like this. Like I said, we could also use potassium, which is K in this problem. And then we have that chlorine. And then this chlorine is going to be bonded to that methyl group. So, just like this. Now, there is one important thing that we need to note about this. When we have a Williamson synthesis, the oxygen in the starting material actually is an alcohol. So we actually have to add a H right here to form the alcohol on both of these, because in the reaction, which we're going to be looking at in part C, the reaction is actually going to take this oxygen away, which is then going to bond that tert-butyl to that oxygen, and that's how we're going to get that final material right there. So let's actually see. I'm going to show us how we do both of these. So I'm going to start with our first example right here, and I'm going to draw it out. So if we have this, and we are going to be starting with that positive and negative ion. So that positive sodium and that negative hydrogen. What we're going to start with is we're going to take these electrons right there. We're going to take that hydrogen away, give those electrons back to the oxygen, which is then going to make that oxygen negative and ready to bond. So let's do that. So if we use these electrons and we take that hydrogen away and then move those electrons from the bond to the oxygen, we are going to actually get this. With a byproduct of Na plus and H2 at this point. But this is where this part of the reagents come into play. So we have and that tert-butyl makes it a little bit messy. But to make this oxygen now stable and not negative, we're going to bond to this carbon right here. We're going to bond that there, and then this bond is going to break and going to leave that chlorine negative, which that's then going to be stabilized by that positive ion. So if we do that, and if we take these lone pairs and we bond it to the central carbon and go just like that, our product is then going to be what we want, which is right here. So it would be this. And that would be our final product, which this is, the full entire molecule, but we could do it in line structures as well. So I'm going to make this smaller, and I'm actually going to show us how we would do, oh, I kind of need that on the plus. And also note that our byproducts would then be, those would be our byproducts. So let's say now we're gonna do this next example. In this next example, we start with this. And same thing, I'm gonna draw out that tert-butyl, which makes it a little messy, but I think it helps to visualize, at least for me it does. And then, once again, this is what we're going to be starting with first, in this first step. And this is the exact same mechanism to make this oxygen go away, and to make that oxygen negative and make that hydrogen go away. We're going to take these lone pairs on those hydrogens, bond to that hydrogen, break that bond, and give those electrons back to the oxygen, which then is going to make this oxygen negatively charged. So let's do just that. And then if we do that, we're going to get this. And this is going to get a little messy, I apologize, because of how tight it is. But just bear with me. I think it's important to see all of these atoms and these bonds, because line structures can get a little confusing. So And then same thing for our byproducts for this. This would be our byproducts. And then this is where this part comes into play. So we have that chlorine bonded to a methyl group. And same thing, we're going to be using these electrons, any of these, from that oxygen, bond it to that central carbon that we want it to bond to, take this bond and give those electrons back to the chlorine, which this chlorine is not going to be negative, but it's going to be balanced by that positive ion right there. So let's do that. If we take those, bond there, make those that way, we're then going to do this. I guess I'll go down. And then our byproducts is then just like that. So those are, depending on what you start with, depends on what your like reaction down here is then going to be, but it's just important to see how there's many different ways that you can solve the same problem. So let me make this a little bigger. Yep, that's fine. All right. So then down here, this next problem is going to be all on the back side of our paper. And this is all based on MCPBAs, which is a metachloroproxybenzoic acid, which this is actually in our notes. So we don't, which we could definitely create this without knowing it. But when we look at the notes, we already know what this MCPBA looks like. And this is exactly what it looks like. And these next questions on this worksheet, this is going to be all of the reagents is going to involve this this molecule right here. And that's MCPBA, metachloroperoxybenzoic acid, which, as you can see, these all have that. So that's what we're really focusing on this last page. So the very important thing is we know how to draw these two starting materials. So let's draw that, and I will then explain the significance of the starting materials. So butene, we know that the ENE makes a double bond somewhere, and we know that but means 4. So it's going to be a 4-carbon chain with a double bond on carbon 1. That's how we decipher that name. So we have 1, 2, 3, 4 carbons in that double bond on carbon 1 right there. Now, the important thing about this mechanism is that this mechanism is going to take these carbons that are double bonded, break one of those bonds, and it's going to use that double bond to create a new bond to an oxygen, which is going to make a ring on the product. And there are many, many ways that you can draw the product based on stereochemistry, and I will show you how that's possible. But it's very important that in this mechanism with the MCPBA and a benzene, that there is a double bond, because that's how this product is going to be formed, because this double bond is going to be broken. And you'll see in this next example that there's also a double bond. So just know that if we are forming a starting material with this reagent right there, the starting material has to have at least one double bond. So for that, this is exactly how this product is going to look. It's going to look messy because I'm going to draw 2 examples with all the molecules and then 2 examples with a line, and show you how you can do it a little differently. So if I broke that double bond and made that ring connected to the oxygen, we then have on dash, we have those hydrogens that the carbon 1 and 2 were originally already bonded to with that double bond. But this first carbon now is also bonded to another hydrogen, which this hydrogen is going to be on a wedge. Now this carbon up here is going to be connected to the rest of the chain, which the rest of the chain is going to be on a wedge. So carbon, now with that being said, you can also alter and flip the wedges and dashes. So there are two possible ways for this example, where then the carbon chain is then on the dashed on that second carbon, and then the hydrogen's on the wedge. And same thing over here. However, it's very important to note that if this hydrogen's on a dash, then this hydrogen's on a dash. Oh. As I'm speaking the wrong thing, I did the wrong thing. And same thing over here. This hydrogen's on a dash, this hydrogen's on a dash. So same thing right here, wedge, wedge. So you can't did like I did originally, because I was going too fast, and mix up and make this hydrogen on a dash. On this example, because they're both hydrogens, it's not too conflicting. But if this was a R group per se, and you switch it around, that would be completely wrong. Now I did mention that there is another way to draw this, where the dash or wedge bond is actually connected to the oxygen. So here's another way that you could draw it, and we discussed this in class. If we kept the line drawing, right? Exactly like this. With that being said, you could also make and flip those so the oxygen is on the wedges or on the dashed, and those hydrogens are on the wedges. And we actually see this in problem 5, but we're not there yet. So another thing to note, the byproduct of this MCPBA is actually going to look like this. You don't like completely need to know that, but it's just a good note to know that one of those oxygens in the middle right here, one of these is actually going to bond and form that ring right there. So just to note. Now this next example, we know how to draw this as well. We have a cyclo, which means ring, hexene, which means 6, and that ene means a double bond on carbon 1. So if we draw that, just like that, and like I said, it's on carbon 1, so you could put that double bond wherever you want, as long as it's just one double bond in this molecule. Same thing, we know that with this reagent right here, this double bond's going to break and form a ring connected to an oxygen. So if we did that, just like this. However, we cannot ignore stereochemistry. So we could, there are multiple ways that we could do this, like we talked about. We could make this a, I'm just going to draw these carbons right here to make it a little bit easier and you could see it better. We could do it like this. And then have the oxygens on that. Or we could do it like this. like that, or we could also do it like this, and we could just simply make the oxygen have the stereochemistry. And like Dr. G said in class, if we did do it like this in the ring and made those dashed and those wedges connected to the oxygen, we technically don't have to do this and do that to the hydrogen, because it's kind of like implicit in a way, like we already know. So depending on what you want to do, it's up to you whether you'd want to do it like this way, or you want to do it like this way, whether you want to then add that hydrogen. Up to you. But there are multiple ways to draw that product, and that's an example of it. Now for number 5, we actually get the product and the reagent, and we have to figure out the starting material. So we know from these past examples, we know that the starting material has to have a double bond. And this double bond is going to be broken to form that ring between the oxygen and the product. Therefore, we know that a double bond has to be right there, because this double bond is going to be what's broken to then form that ring to the oxygen. So we know that part. So we know that this is going to be part of the starting material. Now we have this methyl group that is not relevant to the reaction. So this has to stay there in the starting material. So now, concluding that, we know that this is going to be our starting material. So let's draw that. And because that this methyl group is not involved in the reaction, the methyl group is actually going to stay on that dash, because in both of these it's on a dash. Therefore the starting material has to stay a dash, because it's not influenced by the reaction at all. And that is how we solved week 6 Tuesday's homework.